Hello, welcome back to the first course in general physics. We are still discussing the thermodynamics of systems. And in this lecture, we will continue talking about the thermodynamic processes. After that, we will start talking about the thermodynamics of ideal gases, and we will have the ideal gas equation. We will then consider the problem of the isothermal expansion of an ideal gas, the internal energy of the ideal gas, and then we will be talking about the molar specific heats of an ideal gas. And as we have discussed in the previous lecture, by the end of the previous lecture, we were discussing the types of thermodynamic processes. We have discussed the adiabatic process and the isochoric process, and now we come to the process of constant pressure, or the so-called the isobaric process. In this case, the pressure of the system P is a constant, and in this process, in general, none of the three quantities in the first law of thermodynamics, which are the internal energy, the change in the internal energy, the heat, and the work, none of them is in general zero. However, this process is a controllable process where we can handle it between an initial state and a final state at a constant pressure. Like, for example, if we heat a quantity of water in an open pot, the heating water is a process which occurs at constant pressure because the surface of the water is exposed to the atmospheric pressure. Thus, the pressure of the system is constant. That's called an isobaric process. And in this case, since the pressure is constant, the evaluation of the work done by the system, if its volume changes against the environment from an initial volume to a final volume, which we recall the work done is equal to the integral of P dV from V initial to V final. Since P is constant, we take it outside the integral, and the integral of dV is simply V, the volume between V initial and V final. So P delta V is the work done, and it is easily evaluated. And this is a particularly controllable and an easy process to evaluate the work done during this process, and thus we can evaluate the internal energy from the heat absorbed during this process again. This example will be now discussed when we consider the thermodynamics of boiling water. Suppose that we have a system consisting of 1 gram of water at atmospheric pressure, which is 1.01 times 10 to the 5 Pascal. This is atmospheric pressure. 1 gram of water, pure water, has a volume of 1 centimeter cube, and as it evaporates into the gaseous state, steam, the volume of that 1 gram of water is simply 1,671 centimeter cube. So 1 centimeter cube of water at 100 degrees centigrade, which is the boiling point, is transformed into 1,671 centimeter cube of steam at also 100 degrees centigrade. What are the thermodynamic quantities involved in such a process which occurs at constant temperature, pressure, which is the pressure of the atmosphere, and also during which the temperature does not change? Also, the process occurs at constant temperature, since the only change that occurs is the phase change without changing the temperature of the system. What are the different quantities, and what is the internal energy change of the system as it goes through this process of the evaporation of 1 gram of water? Now, in this case, our system does work on the environment as it evaporates, and the work done, since the process is an isobaric process, is simply P times delta V, and the volume difference delta V is 1,671, which is the volume of the steam in the final state, minus 1 centimeter cube, which is the volume of water of the system when it was in the liquid state. So that means the change in the volume delta V is simply 1,670 centimeter cube. We change it, of course, to meter cube. We multiply by 10 to the minus 6 in order to change the centimeter cube into meter cube. And we multiply this change by 1.01 times 10 to the 5 Pascal, which is the pressure, and we get the result is the work done is equal to 169 joules. That is the work done, which is a result of the multiplication of the pressure by the volume change in meter cube. That's the work done. Now, the heat added to the system during the evaporation or vaporizing is simply the mass of the system in hand times the latent heat of vaporization, and that quantity is m times L sub V. And if we take into consideration m is equal to 1 gram, change it to a kilogram by multiplying it by 10 to the minus 3, because we are using the SI system of units, and plug in the value for L sub V, and that way we get the heat absorbed in SI units is 2,256 joules. The internal energy of the system thus changes by an amount that can be found from the first law of thermodynamics, which tells us that the internal energy change is simply Q minus W, which turns out to be 2,087 joules. This is the internal energy change of 1 gram of water as it vaporizes at 100 degrees centigrade, changing its state from a liquid state to the gaseous state only. And we should remind ourselves that there is no temperature rise in the system. It's just the process is the evaporation of this system from the liquid state to the gaseous state. The other process that we would like to discuss is the isothermal process. Isothermal process, as the name indicates, is a process which is performed at constant temperature. Iso, that means similar or equal, thermal, temperature. Isothermal process. And in this process, as we said, T is constant. The temperature of the system is constant. It occurs slowly enough. We take this transition of the system from the initial state to the final state of volume, temperature, pressure. We take it very slowly or quasi-statically, as we say, in order to ensure that there is a thermal equilibrium at every stage of the process in order to be able to have a viable PV diagram. So this process can be controlled or done as shown in this figure, where we have a cylinder of the gas which is situated on top of a heat reservoir of controllable temperature. So we can fix the temperature of the reservoir, and since the gas is in intimate contact with the reservoir, then that temperature will be the temperature of the gas inside the cylinder. The cylinder has a movable piston, and on top of that movable piston we have a container with lead shot, which can represent the load or the work done by the system as it is lifted up or down. And if we start taking lead shot pieces out one by one, the weight on top of the piston is decreased, and thus the piston rises. The gas expands. And if we do this process at a constant temperature of the reservoir, which is the same temperature of the gas would be, and slowly enough to maintain thermal equilibrium, then this process is the so-called isothermal process. We can also add lead shot, and the volume decreases also isothermally, but in a reversible manner. The gas contained in this container or cylinder, if it is some type of gases, if it is an ideal gas, and we will be talking about ideal gases in a short while, if it is an ideal gas, then its internal energy depends only on its temperature. And thus, for an isothermal process, we have the internal energy change of the system is zero. If we take the system from an initial state to a final state, keeping its temperature constant, then the change in the internal energy of the system is zero, or vice versa. If the internal energy of the system is fixed through a process, then that means the process is an isothermal process. And in this case, the first law of thermodynamics tells us that for an isothermal process, Q is equal to W. So the system absorbs heat and does work on the outside environment. This curve shows processes, two types of processes by which the system is taken from an initial state I to a final state F. The first upper process is an isothermal process where the state of the system changes from I to F at constant temperature T, as indicated by the curve. This is an isothermal process. The other process, the second process, is taking the system from state I to an intermediate state X through an adiabatic process, which is a process through which heat transfer to the system is zero, or from the system is zero. Q is equal to zero. And then after we reach the final volume of the system adiabatically, so we expand the system adiabatically to the final volume, and then we take the system from the final volume Vf and we increase its temperature. We do a constant volume, we take it through a constant volume process from X to F. That way, in these two segments of the processes, or in these two processes, Ix and then Xf, we have taken the system from an initial state to a final state. But as the figure shows, the different ways of handling the process of changing the state from the initial to final involves different values of the thermodynamic quantities. For example, the work done if we do the process isothermally is more than the work done if we do the process adiabatically than isochorically at constant volume. This is just an example. At this point, we would like to deal with the special case of ideal gases, and we will talk about systems containing an ideal gas, as we mentioned a little while ago as an example. And in this case, we will first of all tackle the problem of evaluating the internal energy of the ideal gas and the so-called equation of state of the ideal gas, or the ideal gas equation. Different experiments have been performed on ideal gases, but before we go into the results, we would like to define the ideal gas. The ideal gas is a system of gas that consists of particles that do not interact, they do not collide, for example, with each other. As a special case, we take a system of monatomic gas, a system of gas that each particle consists of one atom. And in the ideal case, we consider the particle of the gas, which is the one atom in this case. That's the monatomic ideal gas. The ideal gas doesn't have to be monatomic, of course, but this is the special case that we are dealing with. The particle of the ideal gas is considered to have 0 dimensions, like a point-like mass. And experiments show that the ideal gas equation is given by the statement P times V is equal to N times R times T, where P is the pressure of the gas, V is the volume of the gas, N is the number of moles of the gas, which is the quantity of material of the gas, the quantity of the gas, and we will be defining it in a little while. R is the gas constant, and T is the temperature of the gas. This is the result of experimental work, and this is the ideal gas equation. The ideal gas doesn't have to be really a hypothetical gas. At low enough densities, real gases that we deal with behave like ideal gases, because all that we need to take into consideration is that they look like point masses in space. So if we take the density of the gas to be low enough, that means the number of particles per unit space volume is smaller with reducing the density. That means the distances between the particles get larger and larger. The average distance between two particles gets larger, and that means the size of the particle itself is relatively smaller relative to the distance between the two particles, and we reach the condition for an ideal gas. The gas constant R, which appeared in the equation of state, is given in SI system by R equals 8.31 joule per mole per Kelvin. Kelvin is the unit of temperature. And what is the mole? We have spoken about the mole, but did not define it yet. The mole is consists of a number of elementary units or particles, elementary particles of the system, and that number is equal to 6.02 times 10 to the 23 elementary units. So if the gas is a monatomic gas, then a mole is equal to, contains 6.01 times 10 to the 3 atoms of that gas, like in the case of argon, or neon, or krypton, or helium, the noble gases which exist in a monatomic form. And this mole, in terms of mass, is simply the molar mass, the mass of this many elementary units of the system. So, for example, the mole in terms of mass for the system carbon 12, for example, the mole is 6.01 times 10 to the 23 atoms of carbon 12, and alternatively, this 1 mole of carbon 12 is equal to 12 grams of carbon 12 isotope. So the molar mass is 12 grams, and the number of elementary units, which is atoms in this case, is equal to 6.02 times 10 to the 23. This quantity, or this number, is called Avogadro's number, after the Italian scientist Avogadro, who have discovered and stated clearly that gases at same conditions of pressure and temperature and volume have the same number of elementary units, regardless of whether these elementary units are molecules consisting of several atoms or of one atom, monatomic gases. Now we discuss the problem of the isothermal expansion of an ideal gas. Since we know what is the isothermal process, we know the equation of state of the ideal gas, then we are ready to discuss the isothermal expansion as applied to an ideal gas. In this case, we recall that from the equation of state, the pressure is equal to nRT divided by V, or it is equal to a constant divided by the volume V, because N is the number of moles, number of molar masses in the sample, and R is the gas constant, which is constant. And since the process is isothermal, then the temperature is also constant. So that leaves us with the pressure is equal to a constant divided by the volume. And now the work done by the system as it expands isothermally is as usual, as defined. W is equal to the integral from V initial to V final of P dV. And now we substitute for P nRT over V, and nRT can be taken outside the integral, and that leaves us with the integral of dV over V. And the integral of dV over V is simply natural logarithm ln V from V initial to V final. And this will give us the result. The work done by the ideal gas as it expands isothermally is equal to nRT times ln V final divided by V initial. That is the work done. And this curve shows the process of the isothermal expansion. For example, we have on the PV curve, on the PV diagram, we have the initial state and final state taken at temperature 310 K. That is an example of the isothermal process. Now, the internal energy of an ideal gas was found from the experimental observations, like, for example, on the free expansion of an ideal gas, which has a constant temperature. In the free expansion process, we have a constant temperature. And since Q and W in the case of the free expansion are also zeros, the first law tells us that the change in the internal energy is zero. Since both the pressure and the volume change, and yet the internal energy doesn't change, but the temperature also doesn't change, That means the internal energy of the ideal gas as it expands freely will only depend on the temperature only, because if it depends on the pressure, then it will change as the free expansion goes. And if it depends on the volume, it will also change, because the volume of the freely expanding gas changes. So since it doesn't change and the temperature stays constant of the freely expanding gas, then we realize that those two state functionals, the energy, the internal energy, and the temperature are correlated. And this statement is that the internal energy depends only on the temperature. The internal energy of an ideal gas is a function of temperature only. And this relation is given by the equation E internal is equal to 3/2 nRT. We can derive this equation from the kinetic theory of gases, but we will not be involved in such a derivation. The only thing that we have to take into consideration is that the internal energy is 3/2 nRT, where R, the gas constant, is simply Avogadro's number multiplied by Boltzmann constant K. Now, at this stage, we are ready to discuss the molar specific heats of an ideal gas. Previously, we have discussed the specific heat and we have defined the specific heat as the heat capacity of a body per unit volume, per unit mass of that body. Now, if we take the unit mass as the mass of a mole, which is the molar mass, instead of taking it as unit mass 1 kilogram, for example, if we take it as the mole, then the specific heat that we are dealing with is a heat capacity per mass, but that mass is not a unit mass, it's the molar mass, the mass of a mole, 1 mole of the system. And this way we call it the molar specific heat. And the molar specific heat is written as a capital C. This is a convention, but we shouldn't mix it up with the heat capacity of a system. And this molar specific heat is equal to the molar mass of the system times the specific heat that we have defined previously, because the specific heat small c is the heat capacity per unit mass. And if we have m unit masses in a mole, then m times c will give the specific heat of a mole of the material. This is the definition of the molar specific heat, where m, capital M, is the molar mass of the system. And if heat is added to the system in order to calculate the specific heat, we can add heat in 2 different ways, one of which is adding heat at constant volume. If the heat is added to the system at constant volume, then we will have the molar specific heat at constant volume, C sub V. That is the molar heat, specific heat at constant volume. And if we add heat to the system at constant pressure while the system maintains its pressure, then the specific heat involved in this process is the so-called C sub P, molar specific heat at constant pressure. And we know how to carry on these two processes. For example, if we fix the volume of the gas and we start adding heat to it, fix the volume by pinning the piston, the movable piston in the cylinder that we have discussed before, that we have seen before. If we pin the piston, then the volume does not change as we introduce heat into the system, and that will be a process at constant volume. However, if we let go and let the piston free to move, but if we don't change the weight on top of the piston, then the gas is at a constant pressure all the time. And as we introduce heat to it, the piston may rise, but the pressure is constant. So this would be a constant pressure process. The relation between these two molar specific heats for an ideal gas is in general, Cp is greater than Cv. It can never be smaller than Cv. And that is a consequence of the first law of thermodynamics. Since we know that Q is equal to the change in the internal energy plus the work done by the system, this is from the first law, and we define the specific heat in terms of the heat absorbed by the system. So in any case, the heat is defined as the number of moles of the system of gas that we are studying times its molar specific heat, and molar specific heat could be either Cv or Cp depending on the process, times delta T. So we have those two relations to depend on, and for the molar specific heat at constant volume, we have Q is simply delta E, because the work done is zero. That is from the first law of thermodynamics. Q is equal to delta E, and thus, since delta E is equal to 3/2 nR times delta T, and Cv is equal, and Q is equal to NCV delta T, equating these two alternative forms of Q, of writing Q equals delta E, or putting Q equals delta E, we will arrive at the result that for a monatomic ideal gas, and I emphasize this is true for a monatomic ideal gas, as the internal energy was defined previously for a monatomic ideal gas. For this case, Cv is equal to 3/2 R, and 3/2 R is equal to 12.5 joules per mole Kelvin. This is the molar specific heat at constant volume for a monatomic ideal gas, that is a gas which consists of atoms, not molecules. And thus we have an alternative form for the internal energy of the ideal gas. We can write the internal energy as E internal is equal to N Cv times T. We replace Cv, we replace 3/2 R by Cv. Now, what is the purpose for this later equation, E internal is equal to NCV? The purpose for it is that the previous form was correct only for a monatomic gas, where the internal energy is 3/2 nRT. But if the gas is not monatomic, if it consists of molecules with more than one atom, then in addition to the translational energy, which gives the internal energy of the system, we have the rotational energy of the molecule, and we have vibrational energies, which will introduce more energy into the system, and then E internal is no more 3/2 times nRT. But this new form of the internal energy, E internal is equal to NCV times T, is correct for any type of ideal gas, whether it is monatomic or it consists of several atoms per molecule, taken into account the correct value for CV, because CV is equal to 12.5 joule per mole Kelvin. That is correct for only monatomic gas. CV for non-monatomic gas will be different than this value. If we make sure to take the correct value for CV, then this relation E internal is equal to NCVT is correct for all systems. The molar specific heat CP at constant pressure is given by is given by the relation Q is equal to NCP times delta T, that's Q, and that is from the first law of thermodynamics, equals to the difference in internal energy, delta E internal, plus the work done. And since the work done is equal to P times delta V, because it's an isobaric process, P is constant, then P times delta V is equal to NR times delta T. We use the equation of state of the ideal gas system to arrive at this result, P delta V equals NR delta T. So plug everything into this relation, and we will get Cp is equal to C sub V plus R. This Cp equals Cv plus R is a correct statement for any system, and if we apply it to a monatomic gas, a monatomic ideal gas, we have Cv equals 3/2 R for a monatomic ideal gas, and thus Cp for a monatomic ideal gas, it's 5/2 of R, but for a general relation, Cp equals Cv plus R. That is the relation between the molar specific heat at constant pressure and the molar specific heat at constant volume for an ideal gas. At this point, I would like to finish this lecture and thank you for your attention.